Oi, calculus. This is the beginning of our integration techniques. There's three types that we're going to focus on. They're kind of the most common. We won't go too crazy with this guy here. Whoops. The partial fractions. And by parts, I'm going to just give you a little 10-question assignment on this one. Okay. The substitution, what this is you need to know those antiderivative rules, like the power rule, the sine rule, the closure rule. We're going to use those. That's what you use. These are techniques to help you solve things where you can't just do those 5 or 6 rules that we learned. Okay, so you'll see as we go along, we're going to use the antiderivative rules from the previous videos to help us do this. But these are techniques to help us solve things where we can't just use a power rule. Okay, so we'll start with substitution. It's like the number one. It's the main go-to. Partial fractions is when you've got a rational functions with polynomials and stuff like that, where there's division of another function. And by parts is something totally different. Okay, where it uses the product rule. But we'll just get into substitution, and you'll notice on the next page here, I'll just flip over to it right now. I've got steps written here, but I figured I'd go through the first example without the steps, and then I'll come back to this one, and then we'll read the steps, and then we'll do this example. Okay, so here we go. So I'm going to use the steps to solve this, but then we'll write the steps out next. So what you do in a case like this where you can't use a power rule, now you could go and expand this all out if you wanted to using Pascal's triangle or binomial expansion, but that would be kind of crazy, and then do the power rule, which would be fine, I guess. But you can't do it because it's a binomial to a power, right? And the power rule is only a monomial thing. So what you do, and I'll do it like this, I'll say, you let u equal some part of the function. Now, I see two things here. This is part of a function. This is one part, or one factor. You'll see it's times. And this times d to the x. This is the other part of the function. Now, there might be something else with the d of x, dx, but there's two things in this question specifically. So I'm going to let u equal something. So what I think I'm going to let u equal is the inside of this guy right here. And you'll see why, because we're going to take the derivative, and all we want left is whatever the other factor is. So in that case, dx. So you'll see I'm going to let u equal 3x plus 1. And what I try to do is I try to let u equal whatever's the most complicated factor in the question. And you'll see as we go through all the examples that I try to emphasize that. Okay, so once I've got my u statement, that's like step 1, is let u equal some part of the function. Now it's going to take the derivative of both sides of your let statement. So I'm going to say the derivative of u is just du equals 3. And then we did that side in terms of x, so dx. And you'll notice there's that dx. Okay, so the next step, after we've taken the derivative of both sides of our let statement, we're going to isolate whatever the other part of the function, of our original function that was left over. So remember, we did the 3x plus 1 inside here. The leftover factor is just dx. So we got to get dx by itself over here. So I'm going to divide by 3. So now that's gone. So now I've got du over 3, or 1/3 du, is equal to dx. So now I can go back and I can substitute all this stuff into place. So I'm going to come back over here. I'm going to say the integral of u to the 5. And our dx is equal to d over 3, so du. And I could put d over 3, but I'm going to factor that 1/3 out because it's a constant anyways. So I'm just going to put it out here. And that's like that constant times a function thing. It doesn't matter. We could leave it there. It's not going to make a big deal because we're going to do everything anyways. Now, we apply the antiderivative rule. So now you can see that we have something we can do the power rule to. So if we think back to the power rule, we add 1 to our exponent and divide by that new exponent. So when I do that, I get 1/3 times u to the 6 over 6, like so. Now, the antiderivative of du is just the 1, so it doesn't really matter there either. Now, we could put the plus a constant and all that stuff as well. So now, that simplifies to u to the 6 over 18 plus a constant right there. So we think we're done because we did the power rule. But of course, this function is in terms of x. We have to put our u, this u, whatever we let u equal, back into the question. So I'll put the final answer, and I apologize for running out of room again, but it's just the limitations. 3x plus 1 to the 6 all over 18 plus a constant, whatever that is, and there is the integral, or yeah, the integral of that 3x plus 1 to the 5. So now, hopefully when you get the steps written out and you see it on the next question, and I think I've got a trig one set up, it'll kind of work out. So remember, let u equal something. I don't know what the best way to tell you, other than I try one. If it works, if it eliminates the other factor, go with it. If it doesn't, erase it, try something else. So here we go. So steps, we're going to let u equal a term in the integrand. So of course, the integrand is whatever you're taking the integral of. 2, we're going to take the derivative of both those sides of our let statement. Then we're going to isolate the leftover factor and dx. So sometimes there's something with our dx, and we'll get to examples like that. We substitute, do the antiderivative, replace it, and we go. So in this question, you're not going to just let u equal cos, because you're taking the cos of something. So you could let u equal cos of something, or you could let u equal just the 4x minus 3. Or in some cases, some people let u equal whatever the other factor is with dx. Usually when it's just dx, though, by itself, you don't let u equal that. Okay, so in this case, if I let u equal cos of 4x minus 3, I like to think, what's the derivative of cos? Well, the derivative of cos is negative sine. Well, there is no negative sign in this question, so I'm not going to let u equal cos anything. I'm going to say let u equal 4x minus 3. So now, that's step 1. Step 2 is take the derivative of both those. So du equals 4. Of course, that's the derivative of x, so dx. There's that guy. Step 3 is isolate my leftover factor and dx. Well, there is no leftover factor in our original question over here. There's nothing else. So I'm going to divide by 4. And there's our dx equals du over 4. So we're going to substitute everything, our u, this guy, and our dx out of the question. So now when I come down here, the integral cos of u du, and of course that 1/4 we had over there, I'm going to factor that 1 over 4. You don't have to do that in this step. You could leave it as du over 4 and take the constant out after, okay? So now I can do the antiderivative of a cos. So let's go do the antiderivative of that. The antiderivative of cos is sine of u, sine of u, like so. I will put the u back in place there now. 1/4 sine of 4x minus 3, and of course plus a constant. And there it is. So following our steps, that one worked pretty straightforward. I'm just trying to find another example that might be a good one to show you guys here. Yeah, let's go let's do this one right here. So this is a good example because it's two factors and a dx or a dt in this case. So I'm going to let u, following my steps, I'm going to let u equal whatever the hardest part of it. Usually you don't worry about the radicals and stuff like that. You just worry about the function. So I'm looking at this question and I see two things. I see a t cubed and I see a t squared. Now you have to consciously be thinking about the derivative. When I take the derivative of a t cubed, in my head, doing mental math, I get 3t squared. Well, there's a t squared left when I do the derivative. So I am clearly going to let u equal the inside of that radical. I'm going to say t cubed minus 1. Because when I take the derivative, I'm going to be left over with the t squared, and I can isolate that factor. So I'm going to take the derivative, I get du. Maybe I should do this in a different color here so we can keep them separate. So I'm going to let u equal t cubed minus 1 du equals 3t squared dt. So now that step where it says isolate the leftover factor and the dx, quote unquote, you can see the leftover factor exactly as it is in the question. And that's what you got to match up. Lots of people will mess this up and it won't be exactly as it. It has to be identical, okay? So I'm going to divide the 3 out of there, like so. So now, when I go back to substitute in, I'm going to have the integral of the square root of u du, and I'm going to take that 1/3 out of there because it's du over 3. You can see that our t squared is there. That's what it's equal to. Du over 3 is equal to t squared dt. Okay? So that's how we end up isolating. So now it's gone. So now I can switch that whole power thing just like we did in the last antiderivative rule stuff. So now, again, when I do this, I get u to the 3 halves, when I add 1, times by 2/3, because I'm dividing by 3 halves. I've got that 1/3 out front still. And then you can have your plus constant, but we'll worry about that after. I'm not too worried about it. It's more about understanding how to do it. So when I simplify this, I get 2/9. We'll substitute the u back in, which is our t cubed minus 1 to the 3 halves plus a constant. And there is your final answer. Okay? Oh. Let's go back here. Let's think about this one now. Now, I said partial fractions earlier is something that you'll use when you have rational functions. Now, I say that, but you only use partial fractions when stuff doesn't simplify. So if it didn't simplify using substitution, then you would use partial fractions. And when you do partial fractions, sometimes you use substitution in it. In this case here, this is a great example, okay, where the two things, the two factors, I'll call them, but they're not factors. Well, they sort of are, but when I look at the two functions, this guy is the more complicated one. And when I do the derivative of that, I can see 2x minus 4. Okay, think about that for a second. The derivative of x squared is 2x, minus 4x, derivative of minus 4x, minus 4, plus 3 is 0. And I can factor that out. I get an x minus 2. I get an x minus 2. So that's the nice part, is I can eliminate it using substitution. So I'm not going to have to worry about this future partial fractions thing that's a little bit more involved. So I want to use the easiest thing that I can. So I'm going to start with u equals x squared minus 4x plus 3. And I'm not using the squared. I'm just using the function itself. Because now when I do the derivative of that, I get 2x minus 4 dx. Again, it doesn't look like I have an x minus 2 dx left over, but when I factor the 2 out of there, I can see the dx, and I'll divide the 2 out now. So that cancels. So now I can see exactly what I have left over, the x minus 2 dx. So now when I substitute back in, I'm going to take that 1/2 right out of there. I've got du left over upstairs. It doesn't matter. You can put it over to the side and have 1 over u squared or whatever you want. You can figure that out. So there's your substituted integral, right? Our du over 2 is there. Check. Our x minus 2 dx is what it's replacing. Check. And we've got our u in the bottom squared. So now when I go and do the integral of that, well, I won't. I'll move the exponent up first, I guess. U to the negative 2 du. Now I can go and add 1 to my exponent, get 1/2 u to the negative 1 divided by negative 1. And then I can substitute everything back in. So I get, that's going to be negative 1 over 2. My u is downstairs now because it's a negative exponent. X squared minus 4x plus 3. And then plus the constant. Okay. Let's see what's our next example here. Okay, this is a, I like the ln examples, or natural logarithm ones, because I always go with the idea that whenever I've got a ln x, I start with u equaling ln x. Okay, that's my hint with this. That's where I start. It might not always work, but that's where I'm going with. So without even thinking, when I see the natural log of x, I let u equal ln x. Because when I do the derivative of that, I get 1 over x dx. You can see that's exactly what it looks like in the question. And that's the idea, is you want it to look identical. You don't want it to have x dx and then think, oh yeah, I've got that. No, it has to be almost a mirror image when you substitute it back in. So now, so when I go back into this now, I've got my 1 over x dx is just du, and my ln x is u, just like that. So now when I do the integral of that, well, the integral of 1 over x is ln x. So I can say, well, ln absolute value, just like our rules said, and then substitute my u term back in there, ln absolute value of ln x, because that's what u is equal to, plus a constant. Now, what's one way we can check to see if this works or is true, is go do the derivative of it. Because the derivative of ln x is 1 over ln x times the derivative of ln x is 1 over x. So it does work. Okay. So I know it seems like a lot, but I'm going to do another video of a couple more examples, just trying to keep adding to it. And then I'll do a third video of just some oddball questions where there's some little twists or tricks to it.